So now we want to talk about heat transfer and the sources of heat transfer and how heat is transferred between substances. And there are three main ways that this happens, okay? And these are conduction, convection, and radiation. So conduction occurs when two things are in physical contact with each other, right? So this is the example of when your spoon, for example, is immersed in a hot cup of coffee or hot chocolate. And if your spoon is completely metal, then the spoon will get warm and it might be hot to the touch. And this is because the spoon is in thermal direct physical contact with the fluid, with the hot chocolate or the coffee. Um, and so heat from the coffee travels into the spoon, and the molecules in the spoon warm up and start jiggling more, and they get thermally excited, or more thermally excited anyway. And that process continues throughout the spoon until the entire spoon is at a higher temperature. Convection is the flow of fluid, and that fluid carrying thermal energy with it. Okay, so this is like air circulating through your home or water that's boiling on a stove. The hot water that's at the bottom of the pan on a hot stove is going to be warmer than the water at the top that's touching the air. So the air is cooler than the bottom of the pan, and so there's going to be a temperature gradient throughout the water. And the water at the bottom, when it starts to boil, hot things like to rise, and so the hot water from the bottom of the pan uh, boils, and that transports the heat from the bottom of the pan to the top. Hot things like to rise, cool things like to sink. And so the cooler water at the top of the pan will then be forced downward and sink, and it will then heat up. And the hot water that had been transported to the surface cools down slightly with the contact with the air, and this process just keeps continuing. The hot boils up from the bottom, the cool sinks, and you get this kind of circular flow inside the water. That's what the bubbling actually is. And then radiation is emission from a source. Okay, radiation is emission from a source. This is heat coming off of the flames of a fire. This would be a wood stove, right, that is radiating heat into a room, or a radiator radiating heat into a room. And these are your three basic mechanisms of heat transfer. Now we're going to focus on heat conduction with this particular example and with this lecture. And I do apologize for all of the busyness already being on the slide here. I had recorded this before, but there was a glitch in the software and it didn't capture the screen. So instead of rewriting all of this, I figured I would just leave it up here. But in any case, all right. So for example, consider this warm reservoir here. All right, I have a warm reservoir right here. And in this warm reservoir, okay, in this warm reservoir is warm air. And we're going to assume that the warm air is at 35 degrees Celsius. Now, what's a reservoir? So a reservoir is a amount of substance that is it has enough thermal energy that if I take a little bit of thermal energy away from it, it really doesn't notice. Okay? And on the other side, I have a cold reservoir, which means that if I dump a little bit of thermal energy into it, it really doesn't notice. Okay? So I'm going to assume that the warm air is outside. This is a really warm summer day, 35 degrees Celsius, and my air conditioning inside is working and it's trying to keep the room at a 20 Celsius temperature. And in between these two, I'm going to have a window made up of glass. Okay? And this window is, you can think of anything that obstructs the connection between two reservoirs as a slab of stuff. And that stuff can be anything. It can be glass, it can be fiberglass, it can be insulation, it can be wood, it can be whatever you want. It's just a slab of stuff. Now, in our case, we're going to say that it's glass. So, how is heat going to move from this hot reservoir to the cold reservoir? Now, remember that heat always flows from hot to cold, right? Heat always flows from hot to cold. And this means that the heat will indeed travel through this obstruction. Now, in most cases with things like glass and insulation, we want to minimize this heat flow. We don't want the heat to flow well at all. If it's warm outside, we want to keep the cool air in. And if it's cold outside, we want to keep the warm air in. And so we want a material that is a fairly good insulator. Okay, we want a material that's a fairly good insulator if you're building a home. There are applications where you may want something that's not a good insulator and you actually want to encourage the flow of heat. But in any case, all right, the flow of heat or the rate of heat flow, right, is given by the amount of heat that's transported per unit time, Q over T. And this is actually a unit of power, okay? Anytime you have energy per unit time, this is heat per time is a unit of power. So the first thing that you might say is, okay, at what rate is heat going to flow through this slab of stuff, our glass? And you might guess, well, it might be proportional to the temperature difference, right? It might be proportional to the temperature difference. And you would be correct. The warmer the air is on one side and the cooler the air is on the other side, the more the heat is going to want to flow through and the system come to equilibrium. You might also say, well, what about the surface area? If there's more area for the heat to flow through, then the heat will flow through better, and you would again be correct. The more the area, the more the surface area that the heat is flowing through, this shaded part right here, and the face on the other side of the cube that you can't see, the more the larger that surface area is that the heat can flow through, the more easily it's going to do so. Or I should say the higher the rate at which it's going to do so. But slabs of stuff also have thickness. And it's not hard to think through and justify the statement that the thicker something is, the more it's going to obstruct that heat flow. And again, you would be correct. So it's actually proportional to 1 over the distance. Or not the distance, but the thickness. Okay? So the thicker my substance is, the more it's going to obstruct the heat flow. And finally, the material itself. Okay? The material itself has what we call a K value, or a thermal conductivity value. Okay? This is going to be your thermal conductivity value. All right? So, thermal conductivity. this basically regulates, or it's a statement of regulation. The thermal conductivity doesn't necessarily regulate. The material regulates the flow, but how the material does so depends on its conductivity. Okay? So a very low K value is a very good insulator. A high K value is a good conductor of thermal power. Okay? And so you put all this together and you get this equation. All right, so the rate at which heat flows is equal to the conductivity times the area times the temperature difference divided by the thickness of the slab of material. And your area is going to be measured in meters squared. Your distance is also going to be measured in meters. The thickness is going to be measured in meters. The temperature difference is going to be measured in degrees Celsius. And so to get the proper units on each side, your thermal conductivity K needs to be joules per second per meter per degree Celsius. Okay? The rate at which heat flows through per meter per degree Celsius. Okay? So, for example, what if we have this 35-degree temperature warm air on one side, 25-degree temperature, or a 20-degree temperature on this side, and glass, if you consult the table in your textbook, glass has a thermal conductivity in those SI units of 0.84, right? 0.84. And we're going to assume that our area of our window is 0.5 square meters and that the thickness is 1 centimeter. Okay? So if the thickness is 1 centimeter, the area is 0.5 meters, then what happens is I plug these values into my equation. So my K times A times delta T divided by the thickness, and I get 630 watts. So what that means is there are 630 watts of thermal power moving through this glass. Now, this is even thicker. 1 centimeter thick glass is a little bit thicker than most home glass, right? If you're just going to build a house and you're putting in windows, this is now bordering on the thickness of really large glass doors and or industrial glass windows. And yet, even still, it has a power of 630 watts, or what that means is 630 joules per second. 630 joules of thermal energy per second are coming in through this window, or is being transported through the window, I should say. And to put that in context, most light bulbs that you could buy 10 to 15 years ago were rated in the 60 to 100 watt range, right? So we're talking about the power consumption of several light bulbs is equivalent to how much heat is being transferred through this substance. Now, one thing to note is that this is a rather warm day. Okay, 35 degrees Celsius is extremely warm. It's warmer than most of the planet gets at any one given time. A typical actual value, more typical value would be something around 30 degrees Celsius, maybe 27 degrees Celsius. That's still a fairly warm weather, really warm summer day. And if I use 30 degrees Celsius, then the rate goes down to 420 watts. But that is still a few hundred watts above a high wattage light bulb. Okay, and so and a square meter is really not or a half of a square meter is really not out of the range of the types of sizes of windows that folks have in their homes. So this is really not a terribly unrealistic example, right? This is really not a terribly unrealistic example. And this is why insulating your home is important. If you had a house made purely of glass, it would be very hard to regulate the temperature. It would be very hard to regulate the temperature. But a well insulated home with a few windows of this size is much easier to regulate, right? It is much easier to regulate. So that is the thermal conduction equation, okay? The rate of thermal energy being transported through a slab of material is going to be equal to the thermal conductivity times the area multiplied by the temperature difference divided by the thickness of the slab, right? And as this example shows, this is one reason why your heating and cooling bills in the summer and winter are what they are. It takes a lot to regulate your temperature. All right, so we will leave you with that, and we will talk to you next time.